take just look at your browser. It will have a few megabytes of code. Look at the database. It will have a few megabytes. Not all the features in that code will always be needed. Should I load the whole thing or not? And if you want to leave the whole thing, so again, the process does have control over what it needs to allocate and deallocate in terms of data, but the process also has code and also has constants, which it doesn't allocate or deallocate. So this is where I'm what I'm attacking right now. Dynamically allocated memory, that's the process's business until the operating system needs to handle it. It needs to extend the size of the image in memory. Then it's again the operating system that has to kick in. So let me give you an example of this principle of locality. This is something that you can all try. And it's about trying to trick the operating system's prediction. Right, allocate a very large array, but make it two-dimensional, a very large two-dimensional array. And then iterate on rows, and then iterate on columns, and measure how much it takes. This iteration will be fast, so you'll need to make it either very large or repeat these iterations many times and compute the sum of the duration. Otherwise, you're not going to see the difference. The truth is that when you iterate on columns, you kind of skip through pages. You don't go nicely through them, and it will take longer because the operating system's prediction will fail. As you jump from one column to another, you're not going to need the next page. You're not going to need some other page. And this phenomenon is very visible if you ever saw MRI rendered data. MRI in Romanian remene is this thing where they put you in a very large tube, magnetic tube, and then they kind of take pictures of your inside, and they're like slices of you. And then you end up practically with a set of images of slices of your body. And if you put these images next to each other, you basically get a three-dimensional matrix. And if you try to render this three-dimensional matrix as a 3D object, when you look at it from a certain direction or another, you're going to go through this data somehow diagonally. You're never going to go aligned through it. And because memory access is so random, these renderers are extremely slow. It took a lot of effort and serious parallelism to get them to work at interactive levels. Let's see, water addict. Is this perhaps the reason why pointers are slower? I'm not sure. I would rather say that pointers require extra calculation because statically allocated memory is directly on the stack and it's contiguous. And static memory cannot be really that large. Okay, you're limited. Yeah, well, a linked list would have to keep referencing. Great, linked list is a great idea. What if your list is split between pages 9 and 10 in the example I have here? So you cycle through the list, right? You iterate through the list. Every single time you have to do a memory calculation for the next element. But then, as you reach the end of page 9 here, you need to bring page 10 into memory and calculate yet another position. So when you iterate through statically allocated memory, that's right next to each other. It's in the stack. You don't really need to do much because it's all in memory already, part of your stack. The other may be somewhere else, but the other is larger. All right, so I think I'll stop here with the principle of locality. And I just want to make sure you get the idea. Principle of locality is something that the operating system uses to predict what page will be used next and bring in from the disk, so that the process would not have to wait for a page load exactly when it needs it. It brings it in advance. Okay, and finally for today, and I'll stop with this, is our two, three, but two mostly. The other one will be for next time. Two approaches for dealing with full memory. So the question here is, what if, in spite of the gigabytes and gigabytes of RAM that I have, I manage to fill it up? Rarely happens nowadays, but I've seen it. I've seen it happen on heavily used servers. What happens then? So all this thing is filled up. No more pages available. Yet a process needs to allocate more memory, or maybe a new process wants to start up. What do you do? Mac OS 9, which I've seen maybe 18 years ago, 17 years ago, in a situation like this, would pop up a dialog saying there is not enough memory to run your program. Please stop some of the programs you're running and try again. It would simply refuse to run to go on with your request. I don't have enough memory. You deal with it. I cannot make it do. Nowadays, they switch to another operating system. Mac OS 10 is not in any way similar to the old one. It's based on a Unix kernel. I think it's a BSD kernel. And what these systems do is they indeed swap memory. You want more memory. I have no memory available, but I do have the swap, which is a disk location where I can spill pages from RAM if I need more. The question is, which pages from RAM do I throw out to swap? Ideally, I would select the pages that will not be necessary in the future, thus having a minimal impact on the execution of the processes. But how do I foresee what page is going to be necessary in the future and which one will not be necessary? And not only that, but these algorithms that I come up with to choose victim pages to throw to swap must be really fast because they are trying to address something that happens very rarely. Not exactly, William. I'll get back to you. So having the memory full and having to swap things out is not something that happens every day. So I can't really afford to do a lot of effort to come up with something that handles that if it only happens once a year. But I still want to be able to deal with it graciously. So I need algorithms that are really low on resource usage and give me a reasonably good prediction on what pages will not be needed. Now, William has suggested that I should kick out the pages of processes with the least priority. Indeed, based on some kind of usage pattern, I will predict the future based on what happened in the past. Now, kicking out the pages of the processes with least priority doesn't mean that those pages will not be needed. If the process with least priority gets CPU, it will need that page, and it will have to kick out something else in order to get it. So really relying on process priority says, you know what, if you're a low priority process, you don't get to execute. But what I'm trying to do is to say, are there pages who are really not needed? There must be some pages who are not really needed in the future. So maybe I move those to the swap. And that doesn't seem to be really related on any priority. You can write your own program that simply adds the numbers from a file, really low priority stuff, right? But you'd still need those pages loaded into memory, even if you're low priority. Because otherwise, I would say I'm killing processes just because they're not important. Not a great idea. Your movie player is not really important. Would you like your operating system to kill it? I don't think so. So, I mean, let's clarify. This movie player that you're looking at right now is extremely important, but others may not be. So, so let's see what would be some ways to do it, some ways to predict the future. So I'm gonna go on with Kopsiman's question, usage pattern. So here is one way of doing it. It's called not recently used. We come up with the following mechanism. Each page gets 2 bits. Every now and then, periodically, these bits get resetted to 0. And then, every time the page is accessed, we put them to 1. If the page is read, we flip one of the bits to 1. If the page is written, we flip the other one to 1. So we'll end up with 4 classes of pages. Pages that were not read or written since the last reset, right? Pages that were only read since the last reset, pages that were only written since the last reset, and pages that were both. So every time I need to choose a victim page, I can look at these classes and I would obviously say, you know what? Pages of class 0, not read, not written recently, are the safest to move to swap. If I've got none of those left, then I have to look at pages read or written. Of these, I would prefer to move to swap pages that were only written recently because reads are much more frequent, writes are less frequent. So then if it was written recently, is less likely to be written again than to be read again. So the next class to move is those only written. The next is those that were read, and eventually the last one, those that were both read and written. So this is a very simple way of predicting which classes will be pages will be used less. Will can be moved to swap with least impact. Another approach, I'll leave FIFO for last time, for next time, is the least recently used. This is a little more involved. This will not only tell you what was recently used and how, it will also try to count how much it was recently used. So here is the mechanism. We maintain a bidimensional array of bits. Okay, we have a matrix of bits. As many columns as pages, as many rows as pages. And then we have the following rule of playing with it. Suppose we have 4 pages in our system. Then we will have a matrix which is 4 by 4. Whenever a page is accessed, we make its row full of 1s, and then we make its column full of 0s. That's the only rule. So when page 0 is accessed, fill up with 1s and then fill up with 0s. Then page 1 is accessed. This is the sequence in which pages are accessed. Page 1 is accessed. Fill up with 1s, fill up with 0s. You can see now that the sum of the values on the page 0 line decreased, right? We have only 2 1s, whereas here we have 3. Page 3 is accessed, page 2 is accessed, sorry. Fill up with 1s, fill up with 0s. Page 3 is accessed, fill up with 1s, fill up with 0s. At this point, page 0 has some 0 on its line. So whenever I need to choose a victim, I can simply choose the page with the minimum sum on its line, because that was the least recently used. The other ones were more recently used because they have more ones. So here is another way of predicting what will happen in a very cheap way that doesn't really eat up loads of resources. Okay, so I will stop here. Next time we'll do the FIFO. We'll do memory allocation within the process, and then we will switch to disk to file system matters, structure, and so on. I think William asked about how malloc, about heap. If you have anything specific about the heap that you need, let me know. Uh, if not, we'll hear each other next Thursday. Thank you. I am glad you liked the story. Good luck with your tests next week. You'll have C programming, processes, and threads. And let's see what else. How is the heap structure also with pages? Okay, I'll address this, William. All of you guys have a great day, and we'll hear each other next week. Good luck with everything. Bye bye.